In this video, I wanted to talk a little bit about combining the worlds of analog circuits and digital circuits. So why do we need to do this? Well, in the last 30 to 50 years, much of the information we deal with in day-to-day life is digital, or is stored digitally or transmitted digitally, which then has to interface with things with other analog signals. So like listening to music over your phone, the music is stored in a digital format, maybe on some server somewhere else, and that digital signal, some binary numbers need to be sent to your phone and then converted to an analog signal, sound waves that we can hear. You can't just send ones and zeros at somebody and expect them to understand what's going on. So we need to be able to convert these signals, and of course, so that's digital to analog conversion. We need to be able to get the music on the computer in the first place, so that's analog to digital conversion. So here's an example of an analog to digital conversion circuit. So this is called a single slope analog to digital converter. So ADC can stand for analog to digital converter or analog to digital conversion. So we're not going to worry about circuit details. I'm just going to show you the parts of this circuit, and we will not worry about any of the nuances, but it'll at least give you an idea of how these kinds of circuits can function. So our input voltage, we are going to send to an op-amp integrator. So the output of this op-amp is going to be the integral of this input signal. So in other words, this input is changing the slope of the voltage here. This we send to a comparator that compares this voltage to a known reference voltage. So this changes its output when our input has been on for long enough and strong enough for this to overtake this reference voltage. This comparator then goes to some logic along with a clock signal that tells this counter when to count, and the counter is connected to some storage that stores our digital bits out. Okay, so basically, depending on how big this voltage signal is, our counter is allowed to count for a longer amount of time and count up to a bigger number if this is larger. So this is the rough idea. And then once that cycle is complete, this logic can do something like reset the counter and drain the capacitor so this cycle can start over again. Again, this is very hand-wavy. Designing this has some designing a circuit like this that works well has lots of nuance to it. There are some improved versions. I think the more common versions are actually dual slope ADCs, but they also are integrating ADCs. They work on similar principles. So anyway, there you have it. In terms of a block diagram, this is going to look something like this. We have our analog voltage in and our digital voltages are the bits of our binary number as outputs. All right, so this kind of integrating ADC is good in that it is very accurate, and you can very easily add a big counter here to give you a precise number at the output. The disadvantage is that it is slow because you are charging up this capacitor and counting while that process is happening. There is an amount of time that inherently has to take. So that makes this type of circuit good for something where you don't care about time very much. Like a great example would be a digital multimeter. So, our multimeters give us a new voltage, 5 times a second, 10 times a second. In terms of electronics, that's a really long time. So you can really easily make you have plenty of time to have a single or dual slope integrating ADC to be able to do a great job, a precise job of that. But if you're doing something like recording audio, most audio is recorded with, I think, 44,000 samples per second. So that's 44,000 voltage measurements you have to make every second, which is, much less than a microsecond. We're talking about much less than a millisecond, tens of microseconds for each of these cycles to happen. So that's a lot of, if you're trying to count up to 1,000 or something in that amount of time for a 10-bit conversion, that could be hard. So for that kind of fast measurement, there is another kind of analog to digital converter called a flash analog to digital converter. And so here we have a reference voltage. So this could be coming from something like a Zener diode. And there is a bunch of resistors in series connected to that. And this is just giving us a big voltage divider with all these different points. So these 4 points are 4 different voltages between our reference voltage and ground. So these are like 4 different intermediate values of the voltage here in order. We can then send each of these to a comparator. And additionally, our input, so this is what we're actually measuring, this gets sent to these comparators also. I'm putting the dots here where the actual connections are. This is being jumped over. This is not a connection, but this is a connection. Not a connection, yes, a connection. Okay, so basically what we have here is, depending on how high this voltage is, some of these comparators are going to be on and some of these comparators are going to be off. There's going to be like a split where it goes from on to off or something like that. So the outputs of all these we can send to some logic gates. This is some combination of logic gates that is going to convert this into our output values. So in this case, if we have 4 intermediate voltages, we only need 2 bits to represent those four different values, Q0 and Q1. You can make, obviously more comparators, more resistors, and more output bits. So this is much, much faster because we're not waiting for any integration capacitor to charge, stuff like that. We are only waiting for this logic to update its state. So if we have fast comparators and fast digital logic, we might be able to get an updated output, depending on our input, in a matter of nanoseconds. Some tens of nanoseconds would not be particularly hard, I think. So yeah, these are much, much faster, not as precise as our integrating ADCs, but anyway, I just wanted to give you guys a flavor of how these sorts of conversions can happen.